440 tons. That is the maximum takeoff weight of a fully loaded Boeing 747. Imagine 300 average-sized cars stacked on top of each other, just floating there in the clouds. It doesn't have helicopter blades spinning overhead, and it definitely isn't filled with helium like a party balloon. So how does a solid block of aluminum and steel defy gravity without falling like a stone? Most people think the engines just push it up, but that's only half the story. The real secret is a shape so simple yet so powerful it literally sucks the plane into the sky. We're talking about squeezing air until it creates a vacuum strong enough to lift a building. To get this, we need to strip away the metal skin and look at the invisible war happening right now. It's a battle of pressure, governed by a rule you might remember from high school physics, Bernoulli's principle. Here is the golden rule. Energy in a flowing fluid is a zero-sum game. You can't have it all. If you want speed, you have to pay for it with pressure. When air molecules speed up, the pressure they exert on everything around them drops instantly. Think of it like a crowded hallway. If everyone starts sprinting, they stop bumping into the walls. Now, look at the cross-section of a wing. Engineers call this shape an airfoil. Notice the design? The top is curved like a hill, while the bottom is almost flat as a board. This isn't an aesthetic choice. It's a trap designed to manipulate the wind. As the plane charges forward at 800 kilometers per hour, the air splits at the leading edge. The air going underneath takes the easy road. It's flat, short, and the air moves relatively slowly. But the air on top, it hits that curve and gets squeezed. To get over that hump and meet the bottom air at the back, it has to sprint. We are talking about a massive acceleration over the top surface of the wing. And remember Bernoulli's rule. High speed means low pressure. Suddenly, you have a region of extremely low pressure sitting right on top of the wing. Meanwhile, the slow-moving air underneath is still pushing up with high pressure. Nature hates imbalance. The high pressure below wants to rush to the low pressure above. Since the wing is in the way, that pressure difference creates a massive upward force. But here is the mind-blowing part. The plane isn't just being pushed up from below. It is actually being sucked up from above. The atmosphere is literally lifting it. That low-pressure zone acts like a giant vacuum cleaner attached to the roof of the plane. This force is called lift, and on a 747, it generates over 4 million newtons of pull. As long as lift is greater than gravity, that 400-ton beast stays in the air. It's a delicate dance. Speed creates the vacuum creates the lift. But what happens when you mess with the airflow? Let's head to the cockpit. Imagine it's takeoff. The runway is blurring by at 290 kilometers per hour. The pilot pulls back on the yoke. The nose rises up. This tilts the wing into the wind, creating something called the angle of attack. A higher angle exposes more of the wing's belly to the wind, boosting that high pressure underneath. More pressure below means more lift. The heavy steel bird leaves the ground. But there is a limit. Push that angle too far and you break the physics. If the nose goes up past 15 degrees, the air on top can't follow the curve anymore. It's like a race car taking a turn too fast. It loses grip and flies off the track. The smooth flow of air detaches from the wing surface. Instead of a smooth vacuum, you get chaos, turbulent, swirling eddies of air. The low pressure zone on top, it vanishes instantly. Without that suction, lift drops to zero. This is called a stall. And remember, gravity never takes a break. The plane is now just a falling rock. The loop is broken. No smooth flow, no speed differential, no lift. To fix it, the pilot has to do the counterintuitive thing. Push the nose down. They need to regain speed and let the air stick to the wing again. How do we prevent this when landing at slow speeds? If you go too slow, you don't get enough vacuum. That's where engineering hacks come in. Look at the wings next time you fly. See those panels sliding out on the back? Those are flaps. They physically change the shape of the wing. By extending down, they make the wing more curved and increase the surface area. This creates extra lift at low speeds, so you don't stall right before touchdown. But there's one more problem: wingtip vortices. High-pressure air under the wing tries to escape to the low pressure on top. It curls around the tip, creating mini tornadoes that create drag. The solution: bend the tips up. These are winglets. They act like a fence, blocking the air from spilling over the edge. This keeps the vacuum intact and saves millions of gallons of fuel. So, the next time you look out that tiny oval window, know that you aren't just riding the wind. You are hanging from a self-generated pocket of low pressure. 400-ton steel miracle, kept aloft by the perfect balance of speed and shape. We beat gravity not with force, but by understanding the rules of the sky. If you want to see how we stop skyscrapers from falling in earthquakes, click this video right here. And don't forget to subscribe to decode more engineering marvels with us.